Where's that bell? Hey, greetings peeps. I hope that sounds really crisp and clear. I've got a new microphone and I can't wait to hear how well it sounds. Hopefully much better and in stereo without doing any funky things. So no more one ear only, but also what's keen is that I don't have to do any post-processing. Okay, HalfaBola time. We have the HalfaBola problem, the one that is basically derived from your book. We're just going to add a few wrinkles to it. The care package dropped from an airplane. And the situation is as such. The airplane travels horizontally with a velocity of 115 meters per second. That's a constant velocity. The altitude of this plane is 1,050 meters. So we want to find the following. We want to find dx, which is the horizontal displacement of the drop package. That's something that the book didn't take care of. They did number 2, which is find the velocity of the package just before it strikes the ground. And what we want to do is find the vertical displacement of the package with respect to the airplane. Okay, so that's the thing. That's what we're going to do with the techniques of projectile motion and analyzing this problem from both horizontal and vertical directions. So we've got to treat them independently. And what we'll do is unite them by time. Time is the great uniter, as we'll see. I drew the situation for us. Here we go. Here's a plane. This is the care package, which quite conspicuously looks something like a bomb, but I guess it would work for bombs too, this problem, if you're in military. But it's really a care package disguised as a bomb. How clever is that? So that nobody would mess with it except for the people who know that the bomb is actually a care package. And here's the situation. We know this is the altitude. We know that dy equals 1050 meters. V naught x is 115 meters per second. And this thing is going to continue on at that constant velocity. So you can see over here in the ghosty kind of image, its velocity is still the same, and it's continuing to move horizontally. That's all it's moving. So V naught y, the original vertical velocity is 0 meters per second because it's not moving vertically. And so what we're going to find here is this dx. How far did it go? Horizontally from the moment that it was dropped to the final landing place. And we want to find the final velocity here and then how far it is from the plane. Okay, the final velocity is like taken care of in the book, but we will do it slightly differently. So what we're going to do actually is the 11-step method, which I think is even neater. And we're going to invoke the 2D motion variables. Yay, our grid. Finally, we can do this in our coordinate system, and then G over here. Let's start filling in some values that we can, that were given to us. I'll get some chalk to do it. Oop, off the screen. Now back. Okay. dx is the thing that we're trying to find. Obviously, we don't know what that is. So right now, this is a big, I don't know what that is, question mark. V naught x, this velocity is completely horizontal, and it's given to us. So V naught x, the original horizontal velocity, is actually 115 meters per second. That was given to us. Ax is always going to be the same in these projectile motion problems because we're not dealing with air resistance either. So there's no horizontal acceleration. There's nothing slowing it down. There's nothing speeding it up. There ain't no horizontal gravity. So we got 0 meters per second squared, which means that Vx is V naught x as always. So we're done with this side. What else do we know? Well, we're told that the altitude of this thing is 1050 meters, all right, 1050. Now it's going to be a negative displacement according to this coordinate system. I didn't write the coordinate system on the drawing. I wrote it over here though. So I know that anything down is going to be negative. So we got negative 1050 meters, like so. The V naught y is going to be 0 meters per second, as we talked about before. It's only moving horizontally. There's no motion in the beginning, that's vertical. So this is 0 meters per second. In fact, it starts off at its peak altitude, so it's not even going to rise above it. So we fill in that value. And so we know that AY, which is equal to the acceleration of gravity, g, is negative 9.8 meters per second squared. That was filled in from before. And Vy equals, well, something for us to solve later. All right. Well, theta in this type of HalfaBola problem, of course, is going to be 0 degrees. That's the nature of this kind of problem. And V naught is the same as V naught x because it's all projected horizontally. The aircraft is only moving in that direction, so we can actually fill this in too at 115 meters per second. Okay? And V we'll deal with later. The thing that we want to find, of course, is time. Time is a great uniter. If you look at your notes, notice bien, indicate that the first thing we really want to find once we get all our values plugged in here is the time. Okay, we used all our keywords like horizontally and stuff like that, and we got these values in here. What's our strategy? Find time from one side and share it to the other. You can't ever, ever, ever combine vertical and horizontal information together. People will do this. It's going to happen. I'm going to mark it really boldly on an exam or something like that. I'll pull my hair a little bit and I'll go, they've mixed the variables. Don't be that person. Don't do it. Do not mix vertical and horizontal. We treat them independently and share them by time. Okay, so here's a strategy. We want to find the time that it takes for the care package to fall to the ground. That is all from the vertical side. Sometimes we can get the time information from horizontal, but we'd have to have everything here to do it, and we don't. So we're going to work from vertical, okay? And this is our dy and our v peak, and basically it's just as a free fall problem. It happens to be projected horizontally, but we're going to treat this part here like a free fall problem and solve for time. To do that, we'll need to choose an equation. All right, so I'm going to set up and get working. All right, so I'm just going to quickly write over here that the v naught y was 0 meters per second, okay, starting at its peak. And we had the acceleration, which is g, is negative 9.8 meters per second squared. And that other piece of information was the dy is negative 1050 meters. Everything checks out in terms of the units. Everything is in MKS, so that's really good. We don't have to do any conversions or anything like that. Okay, so what we want to do is find time. Okay, well, what's an equation that's going to help us find time? Well, we got v naught, we got acceleration, we got d, and we got t. Well, how about this one? You can go through a few. I think the third equation is a good choice over here. And that third equation would be dy. And so notice the subscripts that I'm going to write over here have the y in it to indicate the vertical. And this helps us not mix with horizontal or anything like that. So dy equals v naught y times t. Now t is shared. T doesn't have an x or y. It's its own dimension anyway. And so we don't have to worry about subscripting that. Plus 1/2 g. Now g is implied as only vertical, as we saw in the activity with tracker. The reason why I had you do tracker is so you can clearly see those v versus t and d versus t graphs, and that there was no acceleration horizontally. That was a constant velocity, and we did have accelerated motion where the slope of the d versus t graph changed. It got steeper as the ball, let's say, moved off the cliff. So 1/2 g t squared. All right, cool thing here. We have v naught y is 0, so this whole term just goes away. We don't have to deal with it. And now we solve for t, okay? So t equals 2 times dy. I'm just going to do this all kind of in one step. You know how to do the algebra by now. It's SADMAP divided by g and square root. There it is. Okay, so what's the time at the drop from this peak over here? Well, now we can substitute the values. And so we've got the square root of 2 times dy, which is negative 1050 meters, like that. And divided by g, which is negative 9.8 meters per second squared. Okay, negatives cancel, so I don't have to worry about taking the square root of a negative number. And let's do it on the fly. I think this is probably in the book, but I'm confident enough that I don't need that. I can just do it here. 2 times 10, 50, okay? 2100 divided by 9.8, boom. Square root of 214.28. I'll take the square root of this number here. And answer, I get about 14.6, okay? So this package is in the air for a whole 14.6 seconds. Like so. Excellent. What I'm going to do is fill in the board. Bring up the board and fill in the values accordingly. All right, here we go, board. Where are we now? Well, we got another value. And it turns out that T peak, since we're starting from the peak, is going to be the same thing as T total for the HalfaBola problem. So in this case, since we're only dealing with half of the HalfaBola here, half parabola, the T peak and T total are the same. So 14.6 seconds. 14.6 seconds. Great. All right. Now, what can we do with that information in order to work our way over here to get dx? Because it's a simple step to take now that we have this information. We're going to share it with that side. All right, here's how we do it. Okay, I'm just going to erase, I think. Oh, hold on. Got a little far when I was playing with the board. Okay, so t equals 14.6 seconds. And we get rid of these values because guess what? They're vertical and I want to deal with horizontal. Goodbye. All right. So we had a v naught x equal to 115 meters per second, like that. And we also, let's see, know that, well, ax equals 0 meters per second squared. All right. And that's kind of all we need, believe it or not. I'm going to choose that third equation again, and you'll see why it benefits me. But now I'm going to go dx equals v naught x times t, that's an x, plus 1/2 ax t squared. Okay, so this equation is pretty dandy because I've got time, just found that. I had v naught x from the very beginning, 115 meters per second, and I want to find this. But look, ax is 0. That whole term goes away. So all I have here is this. At constant velocity, this works out for me. No acceleration, pretty easy to do. So dx equals v naught x times t. So that equals 115 meters per second times 14.6 seconds, okay? So how far did it land? Well, let's see. I got 14.6 times 115, and we're looking at about 1.6 kilometers. That's about a mile, all right? So 1.68 kilometers, but we know we want to work in meters, so that's really 1680 meters, and that's just a rounded result like this. All right, we got it. We got it, we got it, we got it. We'll do the other piece next. Okay, excelente. So our dx equals 1680 meters. 1680 meters. Okay, now here's our strategy to get velocity, all right? You know that velocity is going to be two parts, one part horizontal, one part vertical. Here's the horizontal velocity. We've always had it. Click your shoes, and it's 115 meters per second. But we don't have the Vy at the very end. We need to solve for this and then use that in some trigonometry to get the job done. Okay? So we're set with this side. We're back to the vertical stuff over here. All right? And you know, in the process, I just wanted to solve 1, 2, and 3 in order. But sometimes it just helps to solve all the vertical stuff at once and then deal with the horizontal side. But I was just really eager to show you how to share the time. You know, I was kind of excited about that. So Vy is the thing we're going to solve for. So we're going to punch up our vertical values back, which means, guess what? We get rid of these punks over here on the horizontal side. We never want to cross them. They always have a mediator. That's time. Okay, so remember that dy was negative 1050 meters. We remember that v naught y, because it was only horizontal. This didn't move vertically in the beginning, so we have 0 meters per second. And then the thing is that we have, okay, g, or ay, equals negative 9.8 meters per second squared. Well, this is a very easy one. I use the first equation that says Vy equals V naught y plus Ay times t. Knowing that that's g, I'll just throw g right in there. All right, let's plug in. We got V naught y is 0 meters per second plus negative 9.8 meters per second squared times, yes, 14.6 seconds. That's what it takes to fall from before. All right, so I just remembered that, but really we should have had it written down. 14.6 seconds. Okay, therefore, what is Vy? Well, let's find out. All right, so we have, so it's going to be negative, of course, because it's going down. 9.8 times 14.6. And I get 143 meters per second negative. So it's cooking. It definitely picked up a lot of speed from 0 in that 14 seconds, eh? Okay, big time. All right, so let's go for the velocity. Excellent. I'm going to write it on a board, though, so that we have it. Negative 143 seconds for Vy. All right, negative 143 seconds. Meters per second. Bad. Meter per second, like so. And I'll summarize all this stuff in a little bit, but what we're going for is this V. What do we need for that V? We need Vy, and we need Vx, which is V naught x. Same deal. Okay. Redraw. At the very end, we get this situation by the ground. Okay. So here we go. I'm going to draw the ground. Ground, like that. There's the ground. Okay. And the package lands, somewhere around here. It's now looking more like a fish instead of a bomb. Maybe it was just a bunch of fish. I don't know. Okay, so we have this velocity over here, which is the Vy. All right, Vy we got as negative 143 meters per second. And we've had our horizontal velocity all along, like this, as V naught x, which is the same thing as Vx because it doesn't change. It's our starting velocity, 115 meters per second. Okay, so what are we looking for? We're looking for the resultant vector. That's this guy here. All right, how do we do it? Trigonometry. Good thing we learned it before. And if you need some practice on it, you should do it. Find some practice. I'll get you some practice if you need it. But here it is. Okay, so now I've got theta right there. So I'm going to find the angle at which this thing drops, hits the ground, and also the magnitude of this velocity here. All right, let's do the magnitude first. I can totally go with Pythagorean theorem. This is the hypotenuse. And so V would equal the square root of V naught x squared plus V naught y squared. All right, the adjacent side relative to this angle and the opposite side relative to this angle. And now I'll plug in these values. So V equals, we got negative 143 might as well do the order, right? Negative 115, just positive 115 meters per second squared plus negative 143 meters per second. And that whole thing is squared. When you square this, the negative goes away. You add them together. You take the square root. Let's find out what it is. I'm going to see if it matches the book. The book's right over there, by the way. So here we go. We got 115, 115 squared plus 143 squared. Boom. Okay, and then take the square root of that and answer. And if you have the book, you already know the answer. I got 183.5. Let's see what they got in the book. I didn't even bother looking, but yeah, 184. Okay, so 183.5. They rounded it to 184. Let's call that 184 and be consistent with the book. All right, so V is 184 meters per second. We got it. Totally got it. Let's get the angle. All right. Remember, I just learned a new way to write SOHCAHTOA. You can do it like this. It's kind of strange, but it's a little more demonstrative. All right, you can write it like that. Why not? Hey, different cultures. We just did cultural relativism. Some cultures will write forwards, backwards, up, down, have strange hieroglyphics. Some read right to left. We read left to right. And so why not? SOHCAHTOA. So you can see the ratios right here of the sides. And so what should we use? Well, we could use the hypotenuse. We just found it. But we have the two sides here, the adjacent side, relative to this angle being V naught x, and the opposite side. I like to use what we kind of had in the first place. So the book uses cosine. I just prefer this. So what we do here is realize that theta is equal to the inverse tangent of the ratio of the opposite side being Vy over Vx, V naught x, like that, the adjacent side. And so what we have here is theta equals inverse tangent of 143 over 115. And the negative would tell us something about the negative angle relative to the coordinate system that we established. All right, so now let's try this. I'm going to make sure your calculator's in degrees. I'm going to do that right now. It is. Oops. And what if I just change it like that? No, it's still in degrees. All right, so inverse tangent. Boom, inverse tangent of 143 divided by 115. And we got about 51.2 degrees. Does that agree with Mr. Book 51.3? Right on. Yeah. All right, so we got 51.3 degrees. Okay, back to populating all of our values here. All right, so we got 184 meters per second for V. All right, so this equals 184 meters per second. Excellente. And that's the starting angle. And I guess I could put a finishing angle down here too. So just put this down here, maybe theta naught. That looks good over there, theta naught. And so just plain old theta at the very end was the 51.3 degrees. All right, so here's the big picture story. Now our summaries, now basically our ideas of coming up with a discussion statement have much more meaning. We got a lot more to talk about. All right, so our plane, which started at 115 meters per second, horizontally dropped a package at an altitude of 1050 meters. That package dropped down and it hit the ground in 14.6 seconds. When it hit the ground in 14.6 seconds, it had a vertical velocity of negative 143 meters per second because of the acceleration due to gravity of negative 9.8 meters per second squared. It also meant that the package flew a horizontal distance of 1680 meters, 1,680 meters, until it hit the ground and kaput, okay? We also then found that the final velocity, the combined velocity of horizontal and vertical, was 184 meters per second, and that the angle at which it would drop was 14.6 51.3 degrees. So we're having a story that's coming about. And so now we're writing, instead of a sentence or so, the whole thing is summarized by a paragraph. But there's one more thing. Didn't we want to find another piece of information? Yes, and that was, hey, what is the vertical displacement of the package? In other words, how far is the package here from the plane? Well, that's just a trivial kind of trivial question, because if this plane continues at this velocity, so does the package in the horizontal direction. They both have the same velocity, so they track each other. And so what happens over here is that the plane, which is always going to be directly above the package until it hits the ground. So the moment it hits the ground is the full altitude of 1,050 meters. So it didn't have to actually make a calculation there. We just had to know that this plane continued at constant velocity, that the package doesn't drop straight down over here. It moves in a HalfaBola pattern because of the initial horizontal velocity, v naught x, and its landing spot is going to be right underneath the plane. It's going to track underneath the plane the whole time. If you were in the plane, you would just kind of see it drop like that. So we might do a few like simulations that solidify that, and that's what it is. You know, I can't find my bell, but I want to end this somehow dramatically with this new microphone. So what else makes sound? Oh, this lead ball. Ooh. With that, thank you for hanging. HalfaBola solved. Morad out.